Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gil Eapen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gil@eapen.info. My guest today is Professor Raja GuhaThakurta, who is a professor and department chair of astronomy and astrophysics at the University of California, Santa Cruz. His research focuses on galaxies, their dark matter content, cannibalism history, and chemical enrichment as revealed by spectroscopy of their resolved stellar populations. He uses a Hubble Space Telescope and the Keck telescope for his research. Welcome, Raja.
Thank you.
Yeah, thanks for doing this. I want to start with some of your recent work, which hasn't been published yet. Discovery of an extended halo of metal-poor stars in the Andromeda spiral galaxy, in which you say understanding galaxy formation involves look back and fossil record studies of distant and nearby galaxies, respectively. Debris trails in our galaxy's spheroidal halo of old stars provide evidence of bottom-up formation via tidal disruption or merging of dwarf satellite galaxies. But it's difficult to study our galaxy's large-scale structure from within. There's always a problem, right? Unfortunately, we are in the Milky Way. So really deeply understand Milky Way, we have to essentially look outside to something that's comparable. So that's the reason you're looking at Andromeda as a proxy?
That's correct. A good analogy would be, astronomers, being an astronomer is like being stuck in your bedroom for your entire life. The walls of your house are translucent, so you can sort of see into the next room, but you can't see through the house, and you can't see your house from the outside because you've never left your bedroom. But your bedroom has windows, and you can look to your neighbor's house. And if the neighbor's house is close enough, you can see a lot of details of the outside and the interior, perhaps even of your neighbor's house. And that's what Andromeda is. It's our neighbor. It's the nearest galaxy that's larger than our own galactic home. It's larger than the Milky Way.
And distance-wise, how far is it from us?
It's about 2.5 million light years away. In other words, the light we're analyzing today left the galaxy 2.5 million years ago. So we are looking into the past. We are always looking into the past. But 2.5 million years is a very short time in the history of galaxies and the history of the universe. So galaxies typically were formed 10 billion years ago. Now that's 10 with 9 zeros after it. So looking out 2.5 million is really nothing. That look back time is very short compared to the age of the universe and age of galaxies.
Right. So the age of the universe is approximately 14 billion. And so 2.5 million is very, very short period. And Andromeda, I understand, is actually moving toward the Milky Way, right?
That is correct. It's moving towards us.
And so this is, sometimes there's a bit of a confusion. We have a universe that's expanding, sort of a runaway expansion now, accelerating expansion. But in spite of that, you have sort of a physical movement in space-time of Andromeda that surpasses the space-time expansion in such a way that it's actually moving closer and closer to us.
That is correct. So the universe is expanding, but only on average.
Yeah.
That is, on large scales, galaxies are moving apart from each other. And as you said, that expansion rate is getting ever faster with time. There is an active outward push that is winning over the gravity of material in galaxies. Gravity of luminous and dark matter in galaxies is being outdone by this outward pressure of dark energy. That's only true for the universe on average. There are pockets of the universe that are small in astronomical terms. There are small pockets of the universe in which typically gravity has halted the expansion and indeed reversed the expansion. A very good example of that is our own solar system. The sun's gravity is holding the planets in place, meaning they're not static, but the orbital radius is not changing with time. The Earth's radius of orbit around the sun, Pluto's radius of orbit around the sun, these have been frozen. The radius has been frozen by the sun's gravity. So they have completely counteracted the expansion. The Milky Way Andromeda system is an example where our mutual gravity has not just halted the expansion, is leading to a collapse.
So the movement of Andromeda towards Milky Way is really driven by the gravity of the two, the gravitational force between the two galaxies.
That's correct. The mutual gravitational attraction of the two. Andromeda is thought to be a little bit heavier than the Milky Way galaxy, but the mutual gravitational attraction of the two is causing both of them to move towards their common center of mass.
So at some point, I know we haven't gotten to the paper yet, but this is an interesting thing to think about. So at some point, these two galaxies are going to collide.
That's correct.
And so what's our expectation? What's the timeline for that?
The timeline is a few billion years out. Okay. So it's nothing immediate. It's nothing immediate. We have a lot of time to get out of here. No, actually, I'm just only kidding. There's no getting out of here. There is no getting out of here. We have a lot of time to think about it before this collision happens. But the collision is not thought to be catastrophic in terms of the Earth's gravitational bond to the sun. It may be catastrophic for the sun's gravitational bond to the Milky Way. We may get orphaned as a system, the sun and solar system. Even that, there's a very small chance of that happening because the sun is in the inner parts of our galaxy. The outer stars are more likely to get orphaned. But the chance of the Earth getting ripped from the sun are essentially zero. And there's a small chance that the sun and solar system will become an exterior entity. One will no longer be an interior star in the Milky Way galaxy.
That's an amazing thing, isn't it? Even though, when we look at the galaxy, look at Milky Way, you can see millions and millions of stars, but the space between them is so enormous. When two galaxies collide, they're sort of going through each other in some sense, right?
Very much so. The space between stars is vast compared to the sizes of stars. And this is something I teach in my introductory class at Santa Cruz, is if you take the stars in our Milky Way and you shrink the Milky Way proportionately, so the stars are 1 centimeter in size. Let's say each star is a glass marble that's 1 centimeter in diameter. That's the size of a marble, right? As kids, we played with glass marbles. So 1 centimeter marble. If you imagine this shrinking everything so that the sun becomes the size of a 1 centimeter glass marble. Well, the nearest sun, the nearest star to the sun would be 300 kilometers away in that scaled down model. So they're like 1 centimeter marbles separated by 300 kilometers. So you can see why collisions between stars are very rare when galaxies collide. As you said, they literally pass through each other.
Yeah, the collisions are rare, but obviously the gravitational effects are going to be huge. So ultimately, these two galaxies will form a sort of a combination galaxy over a long period of time, right?
That is correct. It'll be like a corporate merger, right?
Yeah.
Two big companies come together, a few people get
Yeah.
laid off. That will happen. A few stars will get orphaned in this process when the two galaxies collide. In
Yeah.
fact, it's those few stars that get orphaned from the Milky Way Andromeda system that carry away energy that allows the rest of the systems to coalesce into a single big galaxy.
Yeah. And so we have a lot of other things to worry about. So a few billion years out, but this will happen before the sun so the sun dies, right? Becomes a red giant. It will happen much before that.
It'll happen around the same time.
Oh,
We think
okay.
the sun is about a middle-aged star. The sun has been
Yeah.
around for 4.5 billion years. In about 4.5, 5 billion years, the sun will bloat up into a red giant. At that point, it will bloat up so much that it's likely to engulf, certainly scorch the Earth, but likely engulf it. So around that same time, the Andromeda galaxy will start to get close enough that it's distorting the shape of the Milky Way, and we'll be distorting its shape. The predictions are the collision will last for a few billion years. It's not an instantaneous collision. It'll be a few billion years between Andromeda's first close approach and the two becoming one galaxy where you can't distinguish the two pieces anymore. That process itself will last for a few billion years, but it'll start around the time the sun is becoming a red giant.
Okay. And because of the gravitational force, I would imagine this movement is accelerating, right?
That's correct. That is exactly
And
right.
so as we get closer and closer, it will become faster and faster.
That's correct.
But the whole dance, as you say, is still going to take a couple of billion years.
That's right.
And so is Andromeda a spiral galaxy as well? It is,
Andromeda
right?
is a spiral galaxy, just like our own.
Yeah. So you have two spiral galaxies merging. So in that case, will we get an elliptical?
We
At the
will
end
get
of
an
it,
elliptical
or
galaxy. In fact, when you have two galaxies that are spirals, but they're comparable in size, the kind of merger it's called a major merger, where the two galaxies are comparable to each other in terms of mass and size. So they will literally destroy the structure and form. Each will destroy the structure and form of the other, and you'll end up with sort of a chaotic set of orbits. Chaotic is not the right term mathematically, but a good way to think of it is a set of bees swarming around a hive, as opposed to a marching band where people are going around on a plane and they're marching in lockstep. So they're all traveling at the same speed, in the same plane, in the same direction around a flat field, say. The spiral galaxy orbits are a lot like marching band. Stars are orbiting in a plane, whereas when you take bees swarming around a hive, each bee is going around the hive because they're attracted to the smell of honey, but no two bees are following exactly the same orbit. They're not in one plane. So elliptical galaxies are like bees swarming around a hive, whereas spiral galaxies are more like well-disciplined marching bands marching around in a plane.
Okay. So I want to get into the paper a little bit. So discovery of an extended halo of metal-poor stars. And so just to set the context, Raja, I don't know a lot about this. The star is basically a furnace that converts hydrogen into helium, and the current generation of stars really has a lot of material in them from previous generations, right?
That's correct.
So some of the heavy elements that we know from lithium onward are either created in some sort of a star blow up, like a supernova or something like that. And so if we look at the composition of stars, it should tell us something, right? Is that the idea?
That is exactly right. So what happens is during the course of their lifetimes, stars produce elements in their interior. As you said, hydrogen to helium is the most common reaction going on at the centers of stars. Near the later stages, when the sun becomes a red giant, it'll be producing other elements in its interior. Things like carbon and oxygen included will be produced, but those remain in the interior. It's really when we study a star in Andromeda or a star in the Milky Way, we are seeing that the light that was generated in the interior of the star, we are seeing that light escape through the last translucent layer of the star. I say translucent, it's not completely transparent, because the elements that are in that outer layer of the star imprint their presence by absorbing certain wavelengths of light. They cause absorption lines, calcium, iron, magnesium. These elements that we are seeing in the spectrum of a star in Andromeda or a star in the Milky Way, these elements that we're seeing were not produced inside the star. Yeah. So what we are seeing is the history of the material that the star was born with. So if a star was born a long time ago in a galaxy, typically there hadn't been much time for chemical enrichment by previous generations of stars. If it was born a long time ago, there hadn't been many previous generations. So the star is born relatively pristine, mostly hydrogen and helium, and very limited quantities of these heavier elements like iron, calcium, etc. On the other hand, if you take the star like the sun that was formed 4.5 billion years ago, there'd been many generations of stars that were born, lived and died before the sun was born. So the sun was born with a relatively enriched medium, chemically enriched medium.
Right. And so if I understand this correctly, Raja, so 14 billion years of the age of the universe, early stars, I would imagine, have all gone, right? The first generation stars, or are they still around?
Some of them are still around. So a lot depends on the mass of the star. If it's a star that's the same mass as the sun, they live for about 10 billion years. So if the star formed 13 billion years ago or 12 billion years ago, and it's the mass of the sun, by now it would have turned into a red giant and is now fading as a white dwarf. If the star is less massive than the sun, let's say it's a half the mass of the sun, the lower the mass of the sun, the longer it lives. And this is a little bit ironic, because you think that the less the mass of the sun, the less the mass of the star, the lower the mass of the star, the less fuel it has to burn. And that's absolutely right. But the amount of fuel is not the only factor that determines how long a star is going to live. Just like the amount of fuel in the gas tank of a Prius is much less than the amount of fuel in the gas tank of a big Hummer, an SUV. Guess which of those vehicles visits the gas station more often? It's the big SUV. It's not how big your tank is or how much gas you have. It's how rapidly you use it and how much gas you have. It's that ratio that's important. And low mass stars tend to be very inefficient in how they are using up their fuel. They don't shine very bright, and so they are actually using their hydrogen to helium very, very slowly compared to a massive gas guzzling star.
Okay, and so we expect the sun is around 4-5 billion years old. It could stay on for another 4-5 billion years. So a total lifespan of 10 billion.
That's correct.
And something less than that, something less than the size of the sun, could stay on for more than that. And so let's say, a star that is half the size of the sun, but could we have had such small stars very early in the history of the universe?
We do. In fact, when stars are born, they are born with a spectrum of masses, and I'm meaning spectrum in a literal, in a figurative sense, not in a literal sense of astronomy. When stars are born, there are typically some big ones, some massive ones, but a lot more low mass ones. And this function that describes the number of stars as a function of their mass is called the initial mass function. So when a cloud of gas and dust fragments, you get a few big stars, but you get lots of small stars. Just like if you took a sledgehammer to a boulder, you'd get a few big pieces, but you'd get lots of tiny grains. So and that's of course taking a sledgehammer to a boulder is not a perfect analogy for how fragmentation works in molecular clouds. But molecular clouds that are dense in molecules fragment collapse under their gravity, they fragment, and you get a few big fragments, but you get a lot of small fragments. So typically when the sun formed out of a cloud of gas, there would have been the formation of a lot of low mass stars as well. And this is true for any star. When stars form, they're typically not formed alone. They're formed in groups, families.
Okay. So those stars, do we call them sort of the first generation stars? Generation means that?
Yes, they would. I mean, if you imagine a galaxy, there's been a lot of research that's going on about the first stars in the universe. And, it's a topic of huge interest because those stars, by definition, would not have had previous generations before them. And so their chemical composition would be quite different from our sun's chemical composition. They would have happened early in the universe's history, because if you give it enough time, the process of star formation is sort of inevitable. It tends to happen. It doesn't start at the same time in all galaxies, but it tends to happen. And so this would have been early in the universe's history that these first stars would have been forming. And there's a lot of research that's going into both trying to identify these stars in our universe using powerful telescopes, but also into doing the kind of calculations that one can do with powerful computers today to figure out what those stars may have looked like in terms of chemical, how they would shine, what their appearance might be. Those two things go together. You predict what they should look like, and you go out and try to look for them.
And the acquisition of materials over time will not be big enough to change their composition. What I'm thinking about is, if you have a lot of asteroids crashing into the sun, and those things have a lot of other stuff
That's
in
correct.
it. But that effect is pretty small in the grand scheme of things.
It is pretty
right?
small just because of the total mass involved in this debris. They're so small compared. Let's say, of course, you're looking at a solar system today that's mostly been cleared out of this material. But it's generally thought that this post-birth sweeping up of material doesn't affect the composition of stars very much. I mean, there's been some interest in what happens when a star swallows a giant planet. Like if you had a Jupiter analog very close to the sun, and if it spiraled in and merged with the sun, would that produce a chemical signature in the sun? That has been a topic of interest. But yes, by and large, when we see stars, we see them with the material, at least what we see in their exteriors is the material they were born with.
Okay. And so we would expect second and third generation stars to have more metal or more heavy elements in them, right?
Certainly as a fraction, yes.
As a fraction. And so this observation that you have in Andromeda, you say discovery of an extended halo of metal poor stars. So what is the implication of that?
The implication, one of the couple of implications. One is there's a very clear trend that people have known about for a long time that my students and I have contributed to a little bit, is you see a very clear trend between how chemically anemic a star is and what kind of galaxy it sits in. It lives in, right? So when you have a galaxy like the Milky Way or Andromeda, generally there's been a lot of chemical evolution in massive galaxies. In low mass galaxies also come in, just like stars come in different masses, galaxies come in different masses. When you have a very low mass galaxy, it tends to contain anemic stars. And the reason this is thought to be the case is relatively simple. The way in which materials, chemicals, get transferred from one generation of stars to another is through the explosion of stars. Stars form material in their interiors, but the material that stays locked in the interior doesn't do any benefit to the next generation. It's the part that is from the outer layers that explode, that get dispersed through the surroundings. That dispersed material is what makes it into the next generation. Now, it's a little, we shouldn't be thinking about finite generation 1, 2, 3, because star formation is a continuous process. So we shouldn't be thinking about a generation as, just like in the human population. In my family, I can identify generations, but if I line that up with your family, our generations are interleaved in that sense, right? So they're not all in lockstep like that. And same is true for generations of stars. But so coming back to this, so if So it's that exploded material that then makes it into the next generation
Yeah.
of stars. So, your question was that, why is it that the stars in the outer part of the Andromeda galaxy, the outer halo, why are they metal poor? Well, I think the simple reason
Yeah.
is we think they came from small galaxies. So why is it that small galaxies, uh, why is it that they have a low chemical content? Let me answer that. And then why is it that the small galaxies are the ones that are contributing stars in the outer parts of the Andromeda galaxy? Let me answer both of those questions. So small galaxies have very low chemical content because when these explosions happen, the amount of dark matter, the depth of the gravitational potential of a small galaxy is so weak that the explosions get blown clear out of the galaxy. So they don't benefit the next generation.
And also, I would imagine just the probability of a supernova happening is also small, right? Because it's just small.
Yes, there are fewer stars, so there are fewer of them that are exploding. But but that is, since you measure chemistry as it's a specific quantity. That is, if you have fewer stars also for that supernova to enrich, so those two exactly cancel out. But it's the fact that the supernova material is not being retained by the galaxy means that efficiency of the transmittal of chemicals from one generation of stars to the next is very low in low mass galaxies, whereas in high mass galaxies where the gravitational potential is deep, the explosion just rains back into the galaxy. It doesn't escape.
So these low mass galaxies, so that's what we call sort of dwarf or
Dwarf
satellite
galaxies and
galaxies.
satellite galaxies.
And so, so how did they form? Is it just sort of a random occurrence that just didn't have enough material?
That's correct.
For those galaxies to be
part of the fragmentation process, just like we said, a single molecular cloud fragments and forms a whole bunch of stars. In the same way as you have on much larger scales, as the material in the cosmic web collapses under, moderated by the gravity of dark matter there, you form large systems, large galaxies, but you form a lot more small galaxies than you form large galaxies. Again, that's just a very generic thing to fragmentation. You typically form a few small fragments, you form a few big fragments and a lot of small fragments.
And same thing has happened in Milky Way too, right? We know of dwarf galaxies sort of in the outer stretches of the Milky Way too.
We see dwarf galaxies that are still intact, and we see dwarf galaxies that are in the process of being disrupted. And this halo of the halo of Andromeda stars we saw really represent the completely digested remains of the dwarf galaxies that Andromeda has cannibalized over its history.
Yeah, so that's the second part of your explanation. So, how did the stars from this dwarf galaxies actually migrate toward the spiral galaxy?
So that process, as we see Andromeda today, there are many small galaxies orbiting it, many of them. Same for the Milky Way. When these galaxies get close to Andromeda, or in the case of the Milky Way, when they get close to the Milky Way, and they can, because they can be on elliptical orbits. They typically are on elliptical orbits. So at close passage, what happens is the near part of that small galaxy is pulled harder than the far part of the galaxy. Because a galaxy, even though it's a small galaxy, it has a finite size. And the near end is pulled harder than the far end just because gravity is a distance-dependent force. That tends to stretch out the galaxy. And once it stretches out, that's a runaway process. So this is called tidal disruption, tides, in the same way that the moon and sun's differential gravity pulls on the near side of the ocean harder than the far side. It stretches the Earth's water into a cigar shape, a very mild cigar shape. It does that constantly. Galaxies do this to each other.
Okay. And so the halo is sort of on the outer parts of the galaxy. What exactly is
exactly that? It's the sparse distribution of stars, sparse and very extended distribution of stars that the central disk and bulge are embedded in. That halo is mostly made of dark matter, but there is a smattering of stars, and it's these stars that we discovered in Andromeda.
Yeah, it's interesting. So we would expect these stars to be sort of old, right? But from a composition perspective, we don't find them to have sufficient amount
That's
of
right.
metals.
Those two things
in
go
them.
together. If they don't have a lot of metals,
Yeah.
that suggests they formed a long time ago.
Right. Okay. And so I'm going back to if the explosions and the material coming out of the explosion cannot be held in the dwarf galaxy because of lack of gravitation. So it's nothing to do with the age of it. It's just that when explosions happen, the heavier metals are not really retained within the stars, right?
That's
It just
correct. There
fly
are these
away.
two different factors that can affect the chemical composition
Yeah.
of a star. For a given galaxy, the older the star, the more chemically anemic it tends to be. But if once you start comparing stars across galaxies, the mass of the host galaxy becomes a very important factor in determining how chemically enriched or not a star is. Those are the two factors. That is the mass of the host, its gravitational potential, and also when it formed. It depends on both of those factors.
Right. Raja, we'll take a quick break. When we come back, we'll talk about your other paper related to surface brightness
Sure.
and fluctuations. Okay, thank you. This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com. So we are back. Raja, we were talking about the composition of stars, the chemical composition of stars. And because we are in the Milky Way, we can really observe a lot of things here. So you have a paper looking at stars in the nearby galaxy called Andromeda. And one of the things you're finding there is that in the outer stretches of that galaxy, you have stars that you say are metal poor. And you have a hypothesis in the paper that those are stars that are formed in the dwarf or small galaxies surrounding Andromeda and then progressively migrated toward that galaxy. You have another paper here on a different subject entitled New Spectroscopic Technique Based on Co-Addition of Surface Brightness Fluctuations, NGC 4449 and its stellar tidal stream. Now, NGC 4449 is a dwarf galaxy.
That's correct.
And so what are we trying to do here in terms of surface brightness?
So what happens is, I'll say a little bit about NGC 4449 first. It's a dwarf galaxy that seems to have recently cannibalized an even smaller galaxy. So that's interesting because, it's like a food chain. Things that are, very low in the food chain still have to eat. So this thing has recently cannibalized a system, and that was discovered independently by two groups. And our group decided that we would try to get spectra of this partly digested remains of the even smaller galaxy that NGC 4449 recently cannibalized. Now, the way things work is when a galaxy is far away, NGC 4449 is about 4 times further away than Andromeda. And when something is 4 times further away, a comparable star in Andromeda versus NGC 4449, the star in NGC 4449 is 16 times fainter. It goes like the ratio of the square it goes like the square of the ratio of the distances. So if something is 4 times further away, you take a light bulb, 100-watt light bulb, place one certain distance away, take another one and move it 4 times further away. The one that's 4 times further away will appear to be 16 times fainter than the one that's closer.
Right.
So, of course, stars get to a certain brightness, the tip of the red giant branch, the stars get to a certain brightness and no brighter. And old stars especially get to a certain brightness and no brighter. And so, how do we deal with this? Because, Already Andromeda is challenging to get spectra of individual stars. That paper we talked about earlier was based on years of hard work with one of the world's most powerful telescopes and spectrograph combinations. So you make the thing 16 times fainter and it's hopeless. So we said we need a new technique. We need a new technique, and we are going to use what are called surface brightness fluctuations to do this work.
So surface. So I have a quick question, Raja. So the galaxy itself is small. Is there any relationship between sort of the distribution of the size of the stars and the size of the galaxy? In other words, do we expect dwarf galaxies to have smaller stars?
No, we don't. We expect them to have the same mix of stars that we see in the Milky Way.
Okay.
What determines the mix of stars is more the age of the population rather than the size of the host galaxy they're in.
Yeah. Okay. And so you were talking about surface brightness.
So surface brightness is just a term that means brightness per unit area. So if you look at a certain patch of the sky, let's say a patch that's the size of the full moon, you can ask, what is the brightness of stars within that area? Brightness per unit area, where area is measured in square degrees or square arc minutes or square arc seconds, brightness per unit area is what surface brightness is. So one of the very interesting things about surface brightness is if you take a galaxy and you move it, you have two galaxies that are, say, twins of each other. And you measure the brightness per unit area in one. You take the second galaxy and you move it, say, 4 times further away. Well, as I said, each star is 16 times fainter in that more distant galaxy. But per unit area on the sky, there's 16 times more stars in that distant galaxy because a particular patch of the sky corresponds to a 4 by 4 times larger area in that more distant galaxy. Those two effects exactly cancel.
Yeah.
So the surface brightness of galaxies are independent of their distance. If you have two galaxies that are identical and one is further away than the other, their surface brightness will still be the same. So that's hopeful. Moreover,
so when you look further away, you have larger area. Isn't the assumption that the galaxy covers that area?
Exactly. As long as you're talking about per unit area that's within the galaxy, you're not going to an area that's too big to go into the outer. If you're looking at a particular, and it's really thinking in calculus terms, it's d brightness, d area. So in the limit when the area goes to 0, in that limit of calculus where the brightness per unit area within the galaxy doesn't change, as you move it further away, particular. But what happens is when a galaxy is closer by, there are fewer. Think of it as a pixel. A given pixel corresponds to a much bigger physical area in a distant galaxy than it does in a nearby galaxy. So it's a balance of two factors. If the galaxy that's nearby, there are fewer stars within one pixel, but each star is brighter than the galaxy that's further away. There are many more stars per pixel, but each star is proportionately faint.
Right. And so the fluctuations in that brightness, that gives us some insights?
That fluctuation gives us a lot of insight because when you have a lot of stars in a pixel, you don't expect the fluctuation to be large. Just the Poisson fluctuation, which is square root of n, where n is the number of stars, square root of n tends to be damped down when you've got a lot of stars in a pixel. So the more nearby a galaxy is, the greater the amount of fluctuation from pixel to pixel. Because in one case, you could have 3 or 4 bright stars in a pixel. In the other case, you've got 100 bright stars in the pixel. And so pixel to pixel, there's not much variation. So these are called surface brightness fluctuations, just from stochastic, counting of stars within pixels. These are much more prominent as you in the most extreme case, you can see the individual stars. But if you can't, you can at least see these fluctuations from pixel to pixel. And that's what we were able to see in NGC 4449. And we trained our telescope to point at some of these upward fluctuations where you have more stars than average in a pixel.
Yeah.
And we said, okay, each star is too faint for us. for our most powerful telescope, but we'll go to the pixels where nature has gathered a few stars for us. We'll go to only those pixels where this has happened. We'll take their spectra, we'll combine them, and we'll get an average spectrum of bright stars in that galaxy. And we use that and we were able to measure the velocity of that galaxy. And we were able to show that this remains, the cannibalized remains of that galaxy are indeed associated with NGC 4449. It's not something in the background or foreground. It's moving at the same speed as NGC 4449.
It's moving at the same speed. And so the same technique also gives you some idea of the metallicity?
It does. It gives us a sense of how chemically enriched or not. And we found that this system was relatively chemically anemic, consistent with the fact that the system that had been swallowed, the galaxy that had been swallowed by NGC 4449, was not a very massive galaxy. It was an even smaller dwarf than NGC 4449.
You have another paper here, Raja. I just want to touch on it quickly. The universal stellar mass stellar metallicity relation for dwarf galaxies. So there is a mathematical relationship that you can derive.
More of an empirical
relation.
relation. This paper was led by one of my former PhD students. He wasn't my PhD student when he wrote this paper, but he was my PhD student before that at Santa Cruz. Evan Kirby led this paper. And what he did was, it was a team of us. We had even a student who had contributed while she was a high school student. She had contributed to this paper, and she's an author on this paper. So what Evan did, the group of us did in that paper, is to look at the chemical composition of stars in a whole bunch of galaxies in the local group. These are small galaxies that are orbiting Andromeda, small galaxies that are orbiting the Milky Way. And we looked at the average chemical composition of stars in a galaxy. That was on the y-axis. On the x-axis was the mass of the galaxy that these stars were living in. And we saw a very clear trend. This trend has been known about for a while, but we were able to extend this down to relatively low mass galaxies. And we saw a very, very clear trend.
Yeah. And so in conclusion, I want to ask you, so you're doing a lot of work in the area of galaxies and their composition, their progression. Any of that gives us some additional insights into this nagging question of what is dark matter and how that is distributed?
Indirectly, yes. What we are doing here in studies of galaxies in the local group, Andromeda, the Milky Way, and its satellites, is we're really looking at the assembly process. We're looking at how galaxies get assembled, and this assembly is mediated by the gravity of dark matter in these systems, whether it's the gravity of the dwarf galaxy that's falling into Andromeda or the collective dark matter of Andromeda itself. We are looking at the gravitational effects of the dark matter, because it's those gravitational effects that are moderating these galaxy collisions and mergers. It's moderating how much material is lost from galaxies during supernova explosions. So we are studying dark matter through its gravitational effects, which is, the primary way in which people study dark matter in astronomy, is through its gravitational effects.
Yeah. So, any of these techniques gives us any higher precision of the mass of the star, or that is not really needed?
The mass of the stars that are.
Yeah. So I'm just wondering. So, given if we have a higher precision of the mass of the galaxy and the mass of the stars, perhaps it gives us a better view as to how dark matter might be distributed. But I guess we already have good techniques to determine the masses, right?
Well, you've hit the nail on the head. Actually, for these low mass galaxies, they are more and more dark matter dominated. That is, when you go to a galaxy like the Milky Way or Andromeda, they contain dark matter. But when you go to these dwarf galaxies, they are very inefficient formers of stars. So their ratio of luminous matter, stars say, to dark matter is very, very low. So they're very, that ratio of how much luminous matter to dark matter there is a measure of how efficiently the system has formed stars. And dwarf galaxies generally have, you could see, a very low ratio of the so-called luminous baryonic matter to dark matter, pointing to a very low efficiency of star formation.
So we don't know what dark matter is, but dark matter has gravitational effects.
That's correct.
Right? And so wouldn't we expect, just like the supernovae, basically getting all the materials out of the dwarf galaxy, wouldn't we expect, because of the lower gravitation, and I'm thinking about Andromeda now, the dwarf galaxies around that, wouldn't the dark matter gravitate toward a bigger galaxy?
Only if it came too close. I mean, so how Andromeda is disrupting stars in the dwarf galaxies is exactly what it's doing to the dark matter in these dwarf galaxies also, because it's a purely gravitational process. So the dark matter in the small galaxy and the stars in that small galaxy are being affected by the same tidal disruption we talked about for stars. It's both the dark matter and the stars in the dwarf galaxies that are gradually getting incorporated into the bigger Andromeda galaxy through these cannibalism events. So Andromeda is eating a visible meal and a dark meal at the same time.
Right. And so the concentration of dark matter in a galaxy is not necessarily a function of the mass of the stars in that galaxy. Is that a correct statement?
I would say that when you say concentration, you mean how much dark matter there is?
It has to be a relative. I guess it has to be a relative ratio.
It's a relative ratio. That's exactly right. No, there does seem to be a trend. The lower the mass of the galaxy, the more dark matter dominated it tends to be.
At least from a ratio perspective. So dark matter over regular matter is higher.
Exactly. Or if you think of it as the fraction of dark matter in low mass galaxies is higher than the fraction of dark matter in a big galaxy like Andromeda.
So that's interesting. So dwarf galaxies could be a better lab for us to study dark matter, perhaps.
In fact, they have been excellent laboratories. That's why they've been of such great interest to astronomers. Dwarf galaxies are some of the best places to look at concentrations of dark matter. And one of the things people have been interested in are there dwarf galaxies out there that are completely dark, but they haven't formed any stars at all? Can you detect them through their gravity? This is sort of one of the open questions in astronomy.
Right. Excellent. Yeah. This has been great, Raja. Thanks so much for spending time with me.
Thank you, Gil.
Thank you.
Bye.
This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.